Hello folks, and welcome to Rational Science. Today we're going to be talking about quarks. Now I think all of you have heard more or less about quarks. Neutrons and protons have three of them. And you always paint them as balls. The quarks and the neutrons and the proton, they're all balls. Now here's the first challenge for you today to think about that. You take three balls, and I want you to tell me how you can make one ball out of three balls, okay? I say it can't be done. You can make a triangle more or less, but you can't make three balls. You can't make one ball out of three balls, okay? So that's the first challenge. But in order to understand what the quarks are, just like neutrino the other day, you need to get into the mind of a mathematician. Mathematician, because they do everything by magic, okay? And for this, we've got to go through a little procedure so that you can get inside the mind of a mathematician. Okay, I want you to understand how a mathematician thinks, because that's going to tell us a lot about how quantum developed and how we ended up with neutrinos and quarks, as well as protons and neutrons. Okay, so here goes. A mathematician goes to the lab, right? He observes something. He observes something invisible. In other words, he doesn't observe, not with his eyes. He sees something happening in there, and he might see some things that are visible, but he doesn't see the invisible forces at work, or mechanisms at work, or agents, Mother Nature's secret agents. He can't see those. He's got to infer those. And a mathematician always infers everything as a particle. Why? Because particle is not a particle. A particle is a number that he can put in an equation. Okay, so you have to understand that as a minimum. There are no particles in quantum mechanics. In other words, they call it a particle theory. It's not. It's not a speck of dust type of theory. It's not a little ball, little bead theory. It's a numbers theory, meaning it's not a theory, it's a description. So it's a numbers description, which they call theory. Okay, and so he goes in there, he goes to the lab, and he sees something visible. And now he's got to figure out what happened there, in that, what invisible forces acted in there. And he goes back to his office. Now he's got to do some calculations. He's going to look at how fast something went, what force, how much mass it might have. Okay, these are the issues that concern a mathematician. Okay, so he goes in there and he sees something, and he puts his first equation. He says A equals B. Okay. But it turns out that B has some parameters, has some properties, okay? So he's going to go in there and he says, okay, it's got charge, which was invented, by Mr. Ben Franklin, the positive and negative. So he's going to give this one a positive charge. And he's going to say, well, it's got a lot of mass. And he might say that it's got a spin, whatever spin is, because, a top can spin maybe clockwise or counterclockwise. He can't deal with that because that's qualitative. He needs to put a number to these things. So he says, well, that's a spin plus one, okay? And I hope you like my hieroglyphics. I hope you learned them by heart, okay? These are very high-level hieroglyphics, so it's very important to understand those signs, okay? And then he goes in there and he puts another variable, or another, could be a constant also, but he puts another factor in there, okay? He's going to call it C, okay? And it turns out that this C also has some parameters, but they're a little different. One might have a negative sign, for example. It's got maybe low mass, very low mass, and it could have a spin in the opposite direction. So he's not going to say it's counterclockwise. He's going to say, well, that's a -1 spin. Okay. So now I hope you keep track of these. It's going to get a little complicated. Okay. And also, it'll be on the test on Friday, so you better memorize them. Okay, so now he needs to put another variable because he observes something in there that is not accounted by these two variables, B and C. So he said, well, something else happened in there, and I can't account for that. So what do I do? Well, what I do is create another variable. And this variable could be anything. It could be energy. He turns that energy into mass, which means particle, which means what? Little ball, which does not mean a little speck of dust. It just means a number. So that's what it is. That's what it's going to be in his equation. So he calls it D, okay? Turns out that this one has a charge of 0. He's got to make it so because he notices that if he puts a negative or a positive in there where it's zero charge, well, it's going to create a problem, because you can't have two positives and one negative, or two negatives and one positive, because then the equation would not, check out. So he goes in there, he said, well, it's got to have a positive, it's got to have a zero charge. And maybe it's got a little bit of mass, because he's got to account for the energy in his system. So he says, well, it has a little bit of mass. And so it doesn't have large mass, or it doesn't have no mass. It just has a little bit of mass. That's what he needs in his equation. So that's what he puts in there. It's not that he found a particle out there. It's that he makes the particle out of nowhere to make his equation come out right. That's all it is. And maybe he determines that this particle has no spin. And I don't know how a top cannot have spin. It either spins or doesn't spin. What does it mean that it doesn't have spin? And again, you have to understand that there is no such thing as spin in quantum mechanics. There is no notion of spin such as what a top does. You spin a top, and we all understand what that means. Or you talk about the spinning Earth, and we all understand that. That's not what spin is in quantum mechanics. In quantum mechanics, it's a very totally different animal, and they don't have a definition for it, not a physical interpretation of what spin is. That's why they have to put the +1 and -1s in there. It's like if you mark the top with a little check mark, with a little, you mark it maybe with your marker, or maybe you cut a little groove in it, and you spin the top. When the top falls down and it's showing the check mark in your face, you call that a 1. If the top spins and the check mark, or the little mark, is on the opposite side of your eyes that you can't see it, we'll call that a -1. And if it's to the left or to the right, you can call it a -1/2 or a +1/2 spin. That's more or less the notion that these people have of spin. So spin, first, has not been defined in physical terms. They don't have the slightest clue what they mean by spin. That's the first issue. The second one is that they have these numbers for these spins. Okay, so spin is not what you think spin is, just like particle is not what a particle is. Okay, they use these words, and they're euphemisms for what they really mean. Okay, so they go in there and they find out that that something else is happening in there. Okay, the mathematician goes in there. He can't figure out that there's another phenomenon going in there that he cannot explain. And he says, oh, what about this? And so he puts another variable. He invents another particle, and this one has no charge, and it has to have no mass, because that's what he observes in the lab. In other words, he says, well, the energy stayed the same, so that means the mass is the same. That means this particle, E, does not have mass. And maybe it can't have charge, because if it has charge, then he's got to invent another particle to counteract it. So he puts a negative or a positive under the E charge. Well, he's going to have to invent another particle that counteracts that one. So far at this point, he says, well, no, it's got no charge, it's got no mass, and maybe the spin is, I don't know, up and down, and he calls that maybe, a half spin. Okay, and you might say, well, where did he get this particle? I mean, was that inside the atom, or where did it come from? And the answer is, it came from heaven. Okay, so that's where it came from. He calls this heaven vacuum, or false vacuum, or he says the seething energy that's in the space all around the collider that he used to accelerate this particle. So he calls this heaven, because this is going to be magic at this point. He says, well, it comes from the vacuum, and this way he covers he kills two birds with one stone. He covers two bases. On the one hand, he proves that the vacuum is made of something, out of mass, out of energy, out of whatever you want to call it, virtual particles. And they come in from the void for whatever reason. They donate their charge, their mass, their spin, whatever they have, and they immediately, within a microsecond, go back to form part of space. Okay, so he gets this particle out of nowhere, because he can't include it inside the atom. If he does, then he's got to account for the energy of the atom. He's got to account for the charge of the atom. He wants to avoid all that. He said, no, it came out of nowhere. And he solved the problem. Okay, so this is how they do it. Okay, and then there's another particle maybe he can't account for. And where did this one come from? Well, I would think that this one came from hell, right? Maybe. Okay, so this is how they do it. Okay, they just invent these particles. And they have to invent them in order to account for observations, what they call observations, meaning that they observe something visible, but they can't see the invisible stuff. And it's the invisible stuff that they have to infer. It's these forces that they have to create, and they have to give values to each one of these parameters, such as charge, mass, spin, for each one of these variables that they introduce. This is how they've created all these particles, you know, throughout the last 100 years. Okay, but then comes the issue of proof. Okay, you got to prove whether this particle really exists or whether it's just a mathematical, you know, contraption. Is this just a hocus pocus, mathematical hocus pocus, or is this some real thing that's inside the atom? And so for that, they have to go to the lab, and this is when they start, you know, they start colliding particles, or so they think. This is what they think they're doing. Okay, and you can see that each one of these traces, whether it's a straight line or a squiggly line, it doesn't matter. They think it's a particle that's moving in there, and what you're looking at really is a trace. Okay, so whether you look at the curlicues or you look at the straight lines, you're talking about particle traces, because they think that what they're doing is smashing particles, and this is the debris. This is what comes out of the hand grenade after it exploded. Okay, this is what comes out of ground zero, and they say, okay, I saw this particle go that way, that went over that way, and what they think they're looking at are traces of these particles through the environment, which is usually a gas, usually hydrogen gas, but they have other gases, I think, as well. They've tried different gases in there. Okay, so what sense can you make out of this? Well, what they say is they go in there and they say, well, hold it. Here you have two particles, okay? If I can get it up here, particle A and particle B. And you can say, okay, particle A went farther than particle B. Then these two particles have different energies. And energy is a different way of saying mass according to Einstein's famous equation, E equals mc squared. So all they have to do is a little calculation of saying, okay, I use so much energy to accelerate these particles, or they take up so much energy, or so much energy was introduced into the system. They get this particle to go this far and the other one to go that far. And so what they do a little calculation. They say, oh, particle A has a different mass than particle B. And they go in there and calculate these masses based on, first, the curvature, second, the distance, okay, and then the energy that they use to move them to the places where they're at, okay? And they do something similar with charge, okay? So here's charge. Give me a second here. C and D, okay? And so you see a curlicue on C and another curlicue on D. Well, let's assume goes clockwise, the other one goes counterclockwise. Okay, so they say, okay, this one is a positron, or a positive electron. The other one is a negative electron, for example, okay? And so what they do is they give negativity to the spin, to the charge, because it depends on which way they're spinning. If they're spinning clockwise, they could be negative charge. If they're going counterclockwise, they're positive charge. And this is essentially how they do it. Okay, and here's an example from real life. Okay, this man, his name was Carl Anderson. He won the Nobel Prize. Let me put him over here and get back in here into the picture if I can. Okay, and he discovered, or found, or whatever you want to call it, made exist the suppositron. They call it the positron. I call it the suppositron, because Mr. Anderson made a supposition. That's what he did. His supposition was that that particle went from south to north, and it went towards the left. So he says, oh, that's not a negative particle. That's a positive particle, because it's going in that direction. And you have these magnets in there, and they should have taken the particle in the opposite direction. Since it went into the left instead of to the right, that's a positive particle. He thinks that's a trace. And so he says that's the trace of a positive particle, and he's going to call that the positron, the one that they were looking for. And so that's how he proved the existence of the positron and got a Nobel for that. Okay, so that's how these things typically work. Okay, and so this is what they think is happening. They think it's they're colliding. They're sending these particles, which they ionize. In other words, they think they're removing an electron from an atom. Okay. There's a process for that. We used to do it in the semiconductor industry. We do it by having a canister with some gas in there. Typically, you remove an electron, or so they think that's what's happening. The ion is positively charged, and now you can move it down the beamline with magnets, because you can manipulate it. Okay, that's the idea behind this. Okay, and this is the same thing that they do at CERN and Fermilab and SLAC and Brookhaven and so on, okay? And so this is what they think is happening. They're thinking that they're shooting bullets at each other when those particles collide. They have one going in one direction, one group of particles going in one direction, the other one in the other direction, as you see on the upper left there. And then they collide them, as you see on the upper right, okay? So these particles are shooting at each other. They make them collide. okay, explode, and then they look at the debris, which is what you saw just a second ago on the traces. What we think is happening is something different. We think under the rope model, what you have is throughout the beamline, you have these atoms, really could be atoms, could be molecules, okay, and they're all bound to each other. They're all merged. Their electron shells are merged into each other, and what they're doing is they're oscillating in place. In other words, they're torquing. The whole serpentine, as we call them, are torquing. So it's a difference between putting two drills against each other versus two guns against each other. There's a difference in the mechanism we're proposing for what's happening inside a beamline. Okay. So this is where they get the idea of particles. Okay. So what is the issue? The issue is that here, when you see these charges go in different directions, they think it's particles that are causing some kind of trace, in a squiggly trace. And the problem I have with this is that, these things are going, according to them, close to the speed of light. And the question is, can something going at the speed of light go in such closed curves as you see there, or in the one that you saw for Anderson? These particles are going very fast. And the question is, can a particle make such closed loops at the velocity of light, or near the velocity of light? So that's one issue you got to ponder, whether that's possible. And so here's the So that's essentially the issue. The issue is whether they are shooting particles, whether they are colliding particles, which is what they think they're doing. They think they're sending particles in opposite directions along this accelerator beamline, and that they're pointing the beams at each other, the rays at each other, and that the particles are colliding there. So it could be an atom. It could be a heavy atom, like they've done it with gold. They ionize gold, they make the gold ions collide, and then they look at the debris, and what they see is tons of particles, certainly more than what are inside the nucleus of the gold atom, for example, quarks, and essentially, protons and neutrons made of quarks. So what they're looking at is quarks. And they have gluons in there that keep the quarks together, and they paint them as these elongated, bubble gums. That's what keeps the quarks from flying apart. But when they collide them, they get gazillions of particles. And they say, well, what we created is a gluon quark or quark gluon soup. They have all these particles, and they say, well, yeah, all those were inside the nucleus of the atom. You say, all those particles, gazillions, because when you see the explosion in there, the photographs that they show, or the computer-generated images, what you see is these explosions with gazillions of traces. And you say, all those were inside the tiny atom? All those particles? And they say, yeah, because they're gluons and they're quarks, and so there's only 3 quarks per neutron and proton. In the case of the gold atom, it's like element number 84 or whatever. And so you can do the calculation. You're going to get maybe 200, 300 particles there. The rest are what, gluons, but gluons are infinite because you get gazillion, you get thousands of particles or explosions there, debris. And so the question is, what are we looking at? What are we staring at? And they claim, yeah, that all those particles are inside the nucleus of an atom. And so they collide them, okay? And then again, you say, well, what did you collide? Did you collide a particle? And it turns out these particles are what? Are numbers. What they're colliding is numbers, because when you say, what does the quark look like? What does a proton look like? Does it look like a ball, like I just showed a minute ago, the 3 balls making one ball? Does it look like a ball? And they say, we don't know what they look like. So because they don't have a picture of what's inside an atom. Even with the atomic force microscope, which is the most powerful thing they have to look in there, they cannot tell you what an atom looks like, let alone what the nucleus looks like. They've never seen the little electron bead going around, which is what people think that these people saw. The laymen, they say, well, yeah, we know what an atom looks like because we've taken pictures of them. But when you look at the pictures, they're all, bird's eye views. You see a little ball at the end of that. They say, see all these little balls? Those are atoms. So we can see atoms. Well, if they're balls, are we staring at a little electron bead going around? Are we taking a picture of a film of a little bead going around? Is that what those balls, those images that we see, is that what we're seeing? Or are we staring at, what we say, which is a membrane, which is a little different than a little ball that's going around, a little bead that's going around, creating traces known as orbits, and the summation of which makes an orbital. Okay, so what are we staring at? And if they can't tell you, if they say, well, it's just a number, it's a number we put in an equation, then how can they be colliding numbers? So it's this duality of math and physics that constantly gets in the way of understanding. Okay, so let's recap from the other day what we had. Here we have a little history of what happened to the neutrino, especially. The original atom proposed by Rutherford and Bohr, and there you see it at the top, it's a little planetary atom, little electron bead going around the nucleus. Okay, so we all understand that. The only issue there is what keeps the electron bound to the proton. You got to account for that from a physical perspective. Mathematically, you can say whatever you want. You can say this one has negative charge, that one has positive charge. You can measure it and say this is 1.6 times 10 to the minus 19 coulombs. Fine, you can do all that stuff. The issue is, please make a movie or of your atom, or a picture of your atom. I want to see a picture of your atom. What are they going to put? And they have to put that atom because they have to explain ionization, they have to explain what you see there, quantum jump, and they have to explain electricity. And for those three phenomena, observations, they have to use this planetary atom. They have no choice. And that's what we use. When someone explains electricity to you, that's the atom he's going to use. So then you ask, is that your atom? Is that how the atom works? I mean, you have a little bead going around. And that's when they say, well, you got to take college quantum mechanics at the university level, maybe master's degree or whatever level, to understand the atom. Yeah, because they're fooling you. They're saying that is not their atom. They deny that atom. Okay? And sometimes they get around to saying, well, that's not our atom, the planetary atom. Our atom means that the bead can be anywhere. Well, that's still the planetary atom. We're saying that there's a little bead next to a bowling ball. I don't care where the little electron bead is. Your atom is a bowling ball with a bead next to it, period. And if that's not your atom, tell me what is. And if that is your atom, tell me what keeps the electron bead bound to the proton. So that's where we start. We start on the wrong foot, and we still haven't changed that in 100 years. We still have the planetary atom in one way or another. And the only thing they have to explain there is the electron bead, why it remains faithful to the nucleus. Chadwick, around 1932, he discovers the neutron. And that was because, hydrogen, you would think that if you go to helium, which is element number 2, well, that should have 2 protons and 2 electrons. Straightforward, right? And it turns out that it did. When they ran that experiment there, they came up with this. Okay, Chadwick and his team, they found out that helium did not equal to 2 hydrogens, but rather to approximately 4 hydrogen atoms. It was 4, not 2. And they couldn't put charges in there, because if they put 2 more protons in there, then they would have 4 positive charges and 2 negative charges of the electrons. So they had to change that, and they say, okay, the guy that's in there has the mass, but it doesn't have the charge of the proton. And that's how the 2 neutrons went into the nucleus of the helium atom. Okay, so this is how the neutron came into being. Okay, then Pauli and first Pauli proposed it, but Fermi was the guy who wrote a paper in 1934, actually, or that's when he published it. And essentially, they came up with a neutrino, and I talked about that last week to explain this beta decay. Okay, the energy simply did not add up. You had to account for the energies in the system. Okay, why it remained constant. And this is more or less what I showed the other day. Okay, so you can see it there. Okay, the explanation was that a neutron essentially gets rid of a boson, which was invented essentially eventually. Okay, the weak force. But his explanation, in other Fermi's explanation, was that there was some particle in there that caused beta decay, and when the electron was spat out, okay, there was this other particle called an antineutrino. And so he played around with the neutrinos and the electrons. The weak force, the W boson there, was invented later on as an intermediate step. So Fermi essentially went directly from the neutron to the neutrino electron. Okay, so he just did that calculation. Okay, and then obviously, then that was a mathematical trick, and the question was whether there was something more, whether that was real. I mean, is there really a neutrino out there? The electron was a done deal, but the neutrino, was this invented just for an accounting process where you have to account for why the atom, when it decays, like a neutron converts into a proton and a proton converts into a neutron inside especially a heavy atom. Okay, and they say, how does that happen? How does this transmutation, this morphing, this metamorphosis? And they say, well, it gets rid of the neutrino, or it acquires a neutrino or whatever. And so they had to account for that by putting the neutrino. The question was, that neutrino real? That was an accounting procedure. Now let's go to the lab and verify that there is a neutrino. That took them several years, okay? And they eventually came up with, in 1970, they were able to prove the neutrino, and there you see it, okay? They exploded another of those explosions inside the chamber. They say it's a collision, and they looked at the particle traces, and they looked at the masses, energy, all this stuff, the speed and distance, and all the stuff they have, all these parameters, and they calculated that one there had to be the neutrino, the one that was spat out by the system. Okay, but the funny thing about it was that they had to make the neutrino have no mass if it was part of the of the atom. Because if you have neutrinos with mass, you may run into trouble in there. But you got to change the mass of the proton or neutron. You have to change the mass of the nucleus. How many neutrinos are there? What do they weigh? Mass. how many particles are they made out of? Okay, that sort of thing. And so one of the ideas was that was proposed and for many years was that it came out of the void. It came out of the sky. It came out of heaven, vacuum heaven. You have to account for this particle, and they said, well, in the process, the neutrino is borrowed. It's a virtual particle borrowed from the vacuum momentarily just to get the equation to come out right. Then it goes back into the vacuum. That was the mechanism. It's called magic, quantum magic. Okay, so they discovered it eventually. Okay, they proven the existence of the neutrino. And they eventually ended up with all these neutrinos, the electron neutrino, the muon neutrino, and the tau neutrino. So they have all these different types of neutrinos, different flavors or whatever you want to call them. Okay, but what happened? After Fermi published his paper in 1934, a lot of people began searching, and they said, well, hold it. The neutrino comes out of the atom or is borrowed from the vacuum, whatever theory you have, okay? But that doesn't explain some of the things that are going on inside the atom itself. You don't have the energy in there to justify what's going on inside the atom with the transmutation. And so they had to come up with something else. They said, look, this still doesn't account for why, for example, protons don't repel protons inside the nucleus, especially that. They said, okay, well, we're not done. There's a difference, because here we have Mr. Chadwick saying, look, there's something called a neutron. A neutrino is another particle that is not the neutron. There's a difference between them. And that's when the Japanese fellow, his name is Yukawa, he came up with a meson. Okay, the meson or whatever, however you want to pronounce that. And he invented that. And he said, well, it's at the time they had no idea of quarks, okay, but that's essentially what they ended up with. They say, look, we have a meson, which is this quark anti-quark pair, okay, and they have a strong interaction, and that's what he described mathematically, and that's what that's why Nobel smiled at him, okay. And he says the following in his Nobel lecture. He says the interaction energy calculated on such assumption is much too small to account for the binding energies of neutrons and protons in the nucleus. Okay? The transition of a heavy particle from neutron state to proton state is not always accompanied by the emission of light particles, photons, right? A neutrino and an electron, but the energy liberated by the transition is taken up sometimes by another heavy particle. Okay? And that's where the meson came in, okay, which in turn will be transformed from proton state into neutron state. Okay, so he was still trying to explain that transformation, and he says, look, there's another particle in there, okay, and we're going to refer to these particles as mesons. Okay, so that's how the meson came into the language. Okay, but it took a few more years to come up with a quark notion, and they started playing with quarks, and they said, well, we have quarks, anti-quarks. And eventually, and they had all different combinations of quarks. Okay, they didn't have a name for it, but they had all these particles that they had in their minds that there's a couple particles in there, etc. And they put them in different combinations. They ended up eventually with 3. Okay, the three quarks. Okay, so because they were able to not explain. Again, we don't have an explanation. What we have is a description, and these are all descriptions. That's why they're not theories; they're just descriptions. And so they said, well, by 1970, they were able to calculate, to figure out, that the neutrino was there. But then what happened? By 1960s, early 1960s, they began to play around with the quarks. They came up with these particles, which eventually were named quarks. Originally, in fact, Zweig, who was Russian. He was born in Russia, but he lived his entire life in the United States. So he studied and did his work in the United States. And in fact, he's still there. And he named them aces. Okay, there was a little fight with one of his mentors. His name was Murray Gell-Mann. And Murray got the Nobel eventually for the quarks and not Zweig. Why? Because they had two different types of notions of what quarks are. And in the case of Zweig, he's really the guy who came up with it, and he claims that he was, or he insinuates that he was robbed of the Nobel by Murray Gell-Mann. What happened was that Zweig went to Caltech, and he studied. He went to Gell-Mann and asked him to be his supervisor for his thesis. And Gell-Mann rejected him. I guess he had too much work or whatever. He said, "No, go and see Feynman." So who was down the hall. And so Zweig went down the hall and asked Feynman to be his advisor, and Feynman agreed, and so they eventually became his supervisor. Okay, so what happened is Zweig started investigating. He went to the lab. He started looking at some of these collisions and doing his calculations, all that stuff, and he came up with the notion of quarks, essentially. And he discussed them with Gell-Mann and with Feynman constantly, for a couple of years. We're talking about maybe 62, 63, 64. By 1964, the idea came out that there were three of them that formed the neutron and the proton. Okay, so this is the idea that was emerging in there. The three balls that make one ball. Okay, and one of the issues there is that, and maybe that's why they gave the Nobel to Gell-Mann, is that there was an issue in the difference of what they were proposing, and I don't think Zweig got the hang of that, and maybe that's why he didn't get the Nobel. Okay, and it's that Gell-Mann had a notion of what is known as the current quark, whereas Zweig had the notion of a constituent quark. And the difference is that when you look at, if you look at those three quarks, the charm, the top, and the bottom, those are heavy. You look at the energies, you'll see they're all in the giga electron volt range, billion electron volts. Okay, and so there is no difference because these are heavy quarks. So there's no difference in their interaction. Why? Because the gluon field does not affect them as much as the gluon field affects the light quarks, such as the up, the down, and the strange. Okay, and so those are known as constituent quarks. What's happening here is they're looking at the interaction between these quarks inside the nucleus and inside the proton, inside the neutron, and how they interact with the gluon and, who knows, the vacuum field, whatever's in the vacuum, all these virtual particles, all these virtual quarks that are flying around in space, I don't know. So they have all this interaction, and that interaction affects the constituent quarks more than it affects the current quarks. Okay? So this was a notion that they were developing. By 1964, we have this notion of a quark. And again, they give the Nobel Prize to Murray Gell-Mann because he's the guy who apparently figured out this key issue of the current quark. Or maybe it's just politics, as it usually is. Because he was down the hall from Feynman, and Feynman had won his Nobel Prize in 65, and Gell-Mann, I don't know when he got his, but he got it shortly after that, because it's like, all these guys, they know each other, and they say, okay, if you vote for me today, I'll vote for you tomorrow. That's why they all have these prizes given to each other. They're all from the same club, okay? And as long as they all repeat the same mantra, about quarks and so on, they're going to get their Nobels, okay? So you got to stick with the catechism, the official catechism. You got to toe the party line. Okay, so what do we have? Well, we have that quark is really an accounting issue. We saw this the other day, and that's what it amounts to. There is no real quark in the sense that there is actually a particle there. They had to look for a particle that fit their preconceived notions. Okay, it was a foregone conclusion, and they had to find it no matter what. Like they're going to find dark matter no matter what. They will find dark matter because they've already proven it in their minds. They have no other explanation for why, a galaxy rotates the way it does. And what they do, they sprinkle all this dark matter on the outskirts, and that's how they get the galaxy to spin the way it does, without the stars flying out, and with the ones on the outside going fast or faster than the ones on the inside. So the only way they explain that is by sprinkling mass on the outside, and they call that dark kilograms, dark matter. Okay, fine. Now they're looking for it in the accelerators, and believe me, they will find it. Someone will get a Nobel for discovering dark matter at CERN or wherever. Okay. But what they did was they had to, so it was an accounting issue. They had to explain why, for example, the proton had charge and the neutron did not if they were made of quarks. How do you account for that? And so they said, well, it's simple. We're going to give 2/3 charge to the up quarks, and we're going to give a negative 1/3 charge to the down quark, whatever that means to you. Okay, so, and why? Because they need it for the accounting procedure only. Okay, that's the only reason for those numbers. And they say if you take 2 up quarks, 2/3 plus 2/3, and subtract a down quark of minus 1/3, well, you get one charge, which is the charge of the proton, which is the opposite of the charge of the electron. We're done. We understand that. Okay, the math. Okay, it matches. And then how about the neutron? Well, if you take 2/3 of an up quark and you subtract 2 1/3, negative 1/3, right, of a down quark, well, you get 0. And now you explain charge with that. Okay. And then they couldn't explain the mass part, but they had the neutrino, and they said, okay, the neutrino comes into the, when the neutron decays to the proton, well, the neutrino enters the phenomena, the transaction, and either it's massless or the mass is borrowed from the vacuum, and we're done. It's just all magic. There's no explanation of the physical mechanism of how this works. It's just accounting. We need a negative charge here. We need a small mass there. That's what we put. We call that a particle, and we put it in the equation. That's only accounting. It has nothing to do with mechanisms. That's the point that I'm trying to make. Okay. Okay. So we ended up with a quark after all these years, and we didn't stop there. What we did, we went with the. We had to look at the forces as well, okay? Because one thing is the particles themselves that form what we call the matter particles, and the other one are these so-called forces, which are turned into particles. Okay? And again, what is a particle? It's a number. That's what a particle is, because you're going to put that number in an equation. So there is no real particle called a force, or a force called a particle. They're not equal. Force is a concept. Particle is like a grain of sand. That's not what it means in quantum mechanics, and unless you understand that, you're in deep trouble. Okay, so what happened? They had to find out why certain forces. They tried to unify these forces. They said we have all these forces. We have the photon, which is the electromagnetic force. Now they had invented the weak force, which was this intermediate particle, or force particle, whatever. Okay, that creates the beta decay, or that mediates, or is an intermediate step in the beta decay. And then they had to hold the proton together. Okay, you had, and how do you do that? If you have 3 quarks, well, you got to hold them together. You have to have some glue to put them together, and that glue was the gluon. That's why they came up with the gluon. And so now you had these forces. The gluon is a force. The weak, the expulsion force from the atom, that's also a force. The electromagnetic is a force, and gravity is a force. And so the quest was on to unify all these forces. How do you unify them? So the first step was to unify perhaps the simplest of them, which was the electroweak, the weak forces with the electromagnetic force. The photon with the weak forces, and there were 2 of them, the W's and the Z's. Okay, and so these guys came around, I think 1970s, there's 1979, or I think that's when they won the prize or whatever. And they came up and they said, hey, look, if you increase the strength of them up to a certain point, at some point these forces will match. Okay, or as I said, the strength of the electromagnetic force becomes the same as that of the weak force. And so they did a calculation. They said, okay, it matches there. And then they went into the lab and they said, well, we confirmed it. Okay, fine. Now, what was the next step? The next step was the grand unified theory. And they said, well, can we unify those forces? And right now, that's what they're working at right now. They're trying to make the accelerators more powerful so that they can create the necessary energies to unify those three forces. Okay. So these fellows won the Nobel Prize. Why? Because they were able to unify the electromagnetic force with the weak force. What does that mean? What have they done? What are we talking about in physical terms? That's the question I like to ask, because we're talking about physics, hopefully, right? And here, let me show you an example. Okay, you're going to unify the only two forces we know. One of them is push, and the other one is pull, because there's no other form of interaction, physical interaction we can imagine. So how these people came up with 4 forces, 2 of which are push and 2 of which are pull, and here you have it. You get it here. Here you have it. Okay, these are the push forces on the left. You got the photon and the weak force, and on the right you have pull forces, the gluon and the graviton. And yes, it gets complicated because the photon it goes back and forth between being a wave and a particle, and particle, a stream of particles. The gluon is a little bed spring there. It's put as a bubble gum between the quarks, and we don't know what those gluons look like, why they look like that, how they are attached to the quarks. There's a lot of questions on the gluon. Why they turn into quarks when you stretch them too far, and so on. There's a lot of questions on the gluon. What is that gluon? Is it a particle? Is it a force? What is it? And then graviton, well, you can take your pick. You can go with particles, which is what the graviton is for quantum mechanics, or you can simulate it with a space-time canvas, trampoline. I call it the fishnet. Okay, so you can take your pick. I mean, how can you reconcile the graviton balls, the little particles, with the bending of space-time? You can't. This is what they're trying to unify. They're trying to make these two equal somehow. And of course, they're going to do it mathematically, or they're trying to do it mathematically. They can't do it physically, as you can see there. There's no way you can reconcile these two mechanisms: the particles versus, the canvas or fishnet. So that's the status quo today. We have the weak and the electromagnetic, in other words, the photon. We have those united at a given energy level. I think it's in the 200 giga electron volt range. You're going to need 10 to the 15th giga electron volts to unify those two with a gluon. And that's what they're working on now. They're trying to get the accelerators to get to those kinds of energies. And the other one is, at 10 to the 19th giga electron volts to get the graviton, because it's so weak at the atomic level. To unify that with the other 3. So one is the gut, which is the strong force with a weak, and a photon with a electromagnetic force. And the other one is the toe, the theory of everything, where you unify gravity with that. But what are they unifying? They're unifying energy levels. They're saying at a given energy level, we have the unification of all these forces. We're talking about a single force, or a single particle, because force is particle, particle is force. Maybe they're a field, the vibration of a field. Who knows what a force is, what a particle is anymore? Why is this important? It's important for them because they can unify that with general relativity. They can tell you that what happened at the Big Bang, or a couple microseconds after the Big Bang. Why? Because they say that's where you have the energies necessary to produce these forces and to split them up. As space-time expanded, all these forces branched out. One became the electromagnetic, the other one the gluon, the other one the weak, and the other one the graviton. So they kind of, each one went their own way. The only way you're going to get them unified is with the energies right immediately, microseconds after the Big Bang. So you see how this is all tied together. Quantum mechanics with general relativity. That's what they're trying to do. Okay? That's what they're working on. Now, the people in string theory, they've got a totally different version. They say, well, no, we forget about all of quantum mechanics. That's kid stuff. We don't do that anymore. We don't deal with gluons. We don't deal with quarks. We don't deal with protons and neutrons. We don't care about that. We're going to deal with the graviton and throw it inside a black hole and find out what happens, especially at the edges. That's the world of so-called mathematical physics, otherwise known as mathematics. Okay, so here are the summary fatal problems as I see with quantum mechanics from a conceptual point of view. And these are just some of them. I got, believe me, I got a longer list than this. Okay, here's my list. Okay, just specifically for what I talked about today. Quantum particles, forces, and fields. What are we talking about? Well, the first thing is that particle is not a particle. A particle is a euphemism. Okay, it's a way of saying, look, I'm talking about a little bead. And as long as you don't ask any questions, I can put that bead and do traces and do whatever I want. I can show it the little particle going through gas, creating this trace, which is what I think that is, right? And so I can say, well, see, this is the trace of a gluon, and that's the trace of a quark or whatever. So that's when they use a little ball. And I always like to say that all they have to do is take a ruler, okay, and measure the width, right? To measure the width of the trace. I mean, if they got that trace, okay, we can figure out the diameter of these little balls, right? The gluon ball, which is what? A force. So I want to measure the width of the force, the diameter of the force. And I can do that really using their own stuff. I'm saying, look, if you say this is a ball that's going through the gas and creating this trace, which you've imaged somehow, very simple. Just tell me what the width of that trace is, and here you have the diameter of that ball. Very simple. It's like if you take a ball and you run it through, I don't know, molasses, right? And you leave a trace. Well, you can tell what the diameter of the ball is. It's just the width of that trace, right? So we can do it. It's just nobody is thinking in physical terms. They all just want to do math. Okay, fields. I showed the other day, they're all superimposed, okay? And here, let me show that again one more time. Okay, we had all these fields, one on top of the other, okay? And you have the background radiation, which is like a temperature field, 3 degrees Kelvin out there, okay? You have all these fields, the electric field, the magnetic field, the electromagnetic field, the gluon field, all superimposed upon each other. And the question is, don't these fishnets somehow get tangled? Okay. So that's one of the issues on fields. What is a field? Is it a physical object or is it a bunch of numbers? So we need a definition or someone to tell us that a field is a physical object. One of the two. If it's, so if it's a physical object, please draw it. I want a drawing of it. I want to know what a field looks like. Okay? And if you're going to draw a fishnet, I want to know what the background that gives contrast to the fishnet is. So you got to identify that as well. And if it's a concept, well, then you can't say that a concept vibrates. You can't say that it's a bunch of numbers. Close to, like the gravitational field, you have the Earth, and the gravitational field extends outwards. Well, if that field is a bunch of numbers that get weaker and weaker as you get farther away, and you get the electric field and you have the magnetic field, and they are the same thing. They get weaker the farther they go out. You're talking about a magnitude at each point in space. That's a concept. You can't say that a magnitude vibrates or that a bunch of numbers vibrate. Okay, so this is the problem. A field is either a physical object, standalone, that you can draw and you can identify all the stuff that's there, whatever's on that picture, or it's a concept. If it's a concept, don't use it in physics. Don't tell me that you're going to vibrate a field and that a particle is a vibration of a field, because you're vibrating a number, and that's irrational. Okay? Then the next one here is the neutrino. Okay, we discussed that. Comes from the vacuum. It's energy that is borrowed from the vacuum. That energy is converted into a particle through E equals mc squared, where m supposedly stands in for the word particle, or the word thing. They're treating mass as a thing, when mass is not a thing. Mass is a concept, especially in the context in which they put it there, which is that E equals mc squared. If mass is equal to energy divided by c squared, velocity of light squared, and energy is a dynamic concept, we have a dynamic concept over another dynamic concept. That doesn't give you a physical object. So mass is not a physical object. It would be to some degree if you say quantity of matter, but that's not the notion they're using. The notion they're using is accelerate the thing and I'll tell you how much mass it has. So mass is a dynamic concept here, and it's exactly the same thing as weight. No difference whatsoever. Okay? Conceptually. Okay, quarks, what are they? Just an accounting procedure. I need 2/3 and minus 1/3 and all this other stuff, to account for why something has charge and the other one doesn't. And also helps me deal with mass, perhaps even spin. Okay, the electromagnetic weak unification. What is that? That's just an accounting procedure. They're saying at such energy, we unify these forces. We unify push with pull. In this case, really push with push. It's two pushes. And they're going to have a little hard time, you know, a little bit of a tough time trying to unify that with the gluon, which is a pull force. And not to mention the graviton, which is also a pull force. That's where I want to see how they unify those forces. Push with pull. Okay? Gut, toe, they're pull forces. Okay? How do you explain pull with particles that are not even particles, they're numbers? I need a physical interpretation. How do you pull with a particle? How do you pull on another particle? That's the issue. Very simple. Okay? Energy is not a thing. It's treated as a thing at all times. It's treated as a thing, especially in relation to with Einstein's equation, E equals mc squared. In other words, in relation to mass. Mass is taken to be quantity of matter for that split second. And people say, okay, I understand mass is a physical object. No, mass is not a physical object because mass is not, first of all, you can't make a picture of mass, period, we're done. But assuming we could say, okay, let's call it quantity of matter, mass is not the quantity of matter or a measure of a quantity of matter. No way, no how. Mass here, as it's used at the accelerators, is a measure of how much energy you need to push an ion or whatever you're pushing. So they look at the energy, how much energy is in that system, and that's how they determine the mass of that particle based on E equals mc squared. So mass is a dynamic concept. It's not quantity of matter. In other words, rest mass. That's not what mass is. Okay, not in the context of what they do in quantum mechanics. Okay, so they've forgotten completely. They threw it by the wayside. The notion of quantity of matter. That's why, you know, Wheeler and Taylor say, all those people who say that, you know, mass is the quantity of matter or measure of quantity of matter, that number does not equal mass. It doesn't, because special relativity especially shows you that if you accelerate something, it increases in mass. Did it acquire more quantity of matter because it went at the speed of light? No, they're talking about pressure of the same quantity of matter. So if you accelerate let's say a neutrino, if you accelerate it faster and faster and faster, it has more mass, more mass, more mass. Okay, so if a neutrino walks a turtle space, it has a certain mass. But if you accelerate it to an eagle pace, then it has more mass. So it's a question of speed, of acceleration. It's got to do with something that is dynamic. Okay? And spin is not spin. It's not the top spinning. Okay, so this notion that they say spin and they insinuate that it's, you know, the little ball spinning, and you say, okay, I understand that. The particle is a ball and it's spinning. That's not what it is in quantum at all, at all. So if that's the notion you have, that's the vision you have, is that what you visualize? You're visualizing it wrong. Neither do we have a particle, neither do we have spin. Okay, spin is more like a mark that you have on the top. And the top, you know, you spin it, and if it points at you, we call that spin 1. If it points in the opposite direction, we call that -1. To the sides, maybe it's half, minus half, maybe it's upside down, I don't know. So spin is not spin, and particle is not particle. Important to know. What have we learned? We haven't learned anything. Not from the mathematical physicists. Okay, we haven't learned anything because they don't have explanations. All they do is look for particles, invent particles really. They don't look for them. They invent particles to fit their preconceived notions. They look at something in the lab that they cannot answer. They see a phenomenon happen, and they say, how was that caused? What forces intervened? They go to the lab, they go to the office really, and they say, okay, I'm going to put a little particle in there that's going to represent some invisible force that intervened in this process, in this phenomenon. That's what they do. And then they look for it. Once they give values, they say, okay, look for it. And they say, well, how many giga-electron volts does it have? Well, I don't know, 12. Look for something that looks like 12 giga-electron volts. The guy looks in there and says, well, here's a trace. And this trace apparently has what we're looking for. It's got, you know, it's a trace that requires 12 giga-electron volts. And they say, okay, what are you going to call it? I'll call it Charlie. Here's your Nobel. That's how it works. That's quantum mechanics in a nutshell.